going back and taking another look at inverse functions. We had a very vague definition of inverse functions in Chapter 1. And we want to kind of make that a little more firm and analytical. Because remember in Chapter 1, it was kind of vague of definition. As we said, you had some function, y equal to f of x, and you just swapped the x and y coordinates, and you got x is equal to f of y, and then in some way you tried to solve that for y. So you got some, if you solve for y, and you got y equal to some other function g of x, that is what we called, y was called our inverse function. Kind of a vague definition, swap x and y. Or graphically, so this is kind of the algebraic approach. And we also looked at it graphically. And if you had some function that looks like this, then you'd say take our exponential function that looks like that. And then if you draw the line y to x, meaning swapping the x and y axes. That's exactly what I'm doing when I rotate about this line y equal to x. So this is my f of x. And if I just take the mirror image about that line, I get another function graphically that looks like that. And we call that the inverse function. So these were kind of vague and they were not very useful, but to get something a little more useful, we needed to introduce more function notation and work with a little bit differently. So let's understand the idea of an inverse function in the first place. So what does it actually happen? So an inverse function has one objective. So you start with some value in the domain, x, and then you apply a function to that, and you get something in the range, f of x. Well, an inverse function is something that's going to take you back to that function. So what you'd like to do is apply this output, this range, into an input of another function. So we have my g of f of x. I'd like to put this function into another function. So that's my domain now is my f of x, and then the range that comes out would bring me back to x, back to where I started. So that's the idea. It undoes what you did. For example, I take x and I take the square root functions. I take the square root of x. And then I put that root of x into a squaring function. So I square my square root. That gives me back to x. It undoes the function. And a square root is undone by a square, and a square is undone by a square root, with some modifications to the domains and stuff to make sure that we're not taking square roots of negative quantities and all things like that. Now the other thing has to be true is it has to go both ways. So if that's my function g, we call g in this case, g is called the inverse function of x. But it also has to work this way, meaning if I start with x and then I plug it into g and I get g of x, I'd have to plug my g of x into f, so I get f of g of x. So that's my input goes into this function. I want to get back to x again. So both of these have to be satisfied. 1 and 2 have to be satisfied. You can see it works over here. For example, if I took my x and then I squared it, and then I put the square into the square root, I get back to x with some modifications. Typically, we use the absolute value, or we specify at the very beginning that x has to be, in this case, strictly non-negative. But that's the idea. This is the idea behind an inverse function. It undoes a function. Just like, in arithmetic, multiplication undoes division, addition undoes subtraction, and vice versa. You can do the opposite and undo the other one. They have to call the additive inverse. Well, these are inverse functions. It follows the same general idea. Okay, right here we can kind of see the workings of our new definition. So instead of this vague one, a process one, both of these are process-oriented things, follow this process. We'd like a testing one, an analytical testing approach to determining if two functions together are related as inverse functions, meaning they undo each other. And we find that's very important in all of mathematics. If you do an operation, you want to be able to undo what you did and get back to where you started. And it gives you a path to do that. So here's our new definition of an inverse function now, which is different than the other one. We're going to be a little more precise over here. And says let's see what the functions f of x and g of x are inverse functions of each other, or inverse functions. That's what we're defining over here, inverse functions of each other. If precisely this happens, if I do the following. If I take the composition f composed with g of x, and that's equal to x, and g composed with f of x is also equal to x. And we call g of x, we just use the notation, and we call g of x, I could do the same for f or g of x, f inverse x. That's the notation we're going to be using. So this is our test. If two functions satisfy both of these properties, they are inverse functions of each other, meaning they undo each other. So I can take one and then take the other, and I'm back to my argument. It undoes my function by getting me back to what I first put in. Put this in, I get f of x out. Put f of x into g of x, and I'm back to my starting x value. It undoes everything I've done up to that point. Okay, so what we want to do here, what we want to be able to do, is simply test to see if two functions are inverse functions or not. Let's see how we might apply this now. Here's our definition. Let's take a look at an example. And it kind of makes sense now. You're undoing the function. It just looks abstract in this notation, very mathematical notation, but that's all it's telling us. Now, there are still some questions that we will work out as we go along here about domains and ranges, but we know about domains and ranges of functions, so we can kind of work those details out as we go along. Roughly speaking, let me just make that point first. Roughly speaking, we can see what happens. This is not precise because sometimes you have to restrict the domains or the ranges restrict. But roughly speaking, if you have your two functions, f of x and its inverse, so this has a domain over here and the range over here. The domain and range of that function. Well, what did I do? Remember, I swapped the x and y coordinates. That's what made it work. So roughly speaking, not exactly, because you might have to do some restriction, the domain over here becomes the range of that function. Because remember, this is x, y. These are the x, y values. X and y, the inputs and the outputs. And the range of the function maps to the domain over here. So I say it's roughly speaking because we may have to, change some things around to make it work out. We may have to restrict the domain or the range of one or the other to make it work out. And it also goes back in the other direction. So it goes both ways. So that's the one thing you look at. So you can see their domains and ranges flip, roughly speaking. And we'll kind of take a look at that as we go along over here. Okay, so that's another important point that we need to be aware of. Now let's take a look at some examples. How do we test? How do we apply this test to see if two functions are indeed inverse functions of each other? And then we'll also talk about the domains and ranges of each of these. So let's take f of x is equal to 2x squared minus 1. And then my other function, g of x, is equal to the square root of x plus 1 over 2. Okay. Let's first start off and see about the domains and ranges of each of these. Well, this is the polynomial, so do that for a second. I want you to take the time, find the domains and ranges of each of these. That's on the test on Thursday, so see if you can ascertain from those their domains and ranges. I'll give you a minute to work on that. Here's where you can see a slight change in where it's slightly restricted, but you'll see something similar over here. You don't get that quite correlation over here. That's why I said there's a little bit of a restriction going on over here. Does everyone see how I did that? Here, just plug this in and see the graph of that. Plug it into your calculator and you get something that looks like this. And visually, you can see y starts down here at -1 and goes up to infinity. So y is greater than or equal to -1. Here you can see the range of this thing over here. So x looks something like this. That's what that looks like. Use your calculator. You can plug those things in, a nice picture of these things. They're simple functions. Okay. So now let's take a look and test it. Let's take and do our inverse function test. Are they inverse functions? You do see these correlate, but these are kind of not quite there because it's a restricted domain. And I'll talk about that when we look at the picture. So here, inverse function test. So you already know how to do this, so try this. I want you to do f composed with g. Plug that in and see what you get. So take my function f, and where we have an x, put in your g of x. As well as this, g composed with f. Do those two compositions. And hopefully, you're getting this out. Does anyone want to see how I got both of those to be x? And just raise your hand. Okay, let me just take a look at the first one. Remember, what is it? It's f composed with g. This is equal to f of g of x. I should have been practicing this on the homework. So what is my function f? I look at my outer function, and that is 2 times the input squared minus 1. Okay, that's what my function f looks like. F of blank is 2 times blank squared minus 1. But what is my input? Well, my input now is my function g of x, which is the square root of x plus 1 over 2. So what happens? The square cancels the square root. It gets rid of that square root. So what happens over here? This becomes equal to 2, and it just becomes x plus 1 over 2. They cancel each other out, minus 1. Okay, now I can distribute the factor of 2. This 2 cancels with that 2, and then I simply write it out as x plus 1 minus 1, so just x. The first thing is solved. While we're at it, let's take a look at the other one. So now I'm going to plug in over here, 2. So now that's g composed with f, and that's g of f of x. So what is my g function? It's a square root. This is what it is. It's a square root of my x value, which is my input. Then I add 1 to that, and then I divide by 2. Well, what is my input over here? It is now 2x squared minus 1. Well, I can just drop the parentheses over here. That becomes the square root 2x squared minus 1 plus 1, so it's just 2x squared over 2, which is simply equal to, let me just kind of put it right here, the square root, because the 2's cancel, of x squared, which is really the absolute value of x. That's where we're going to have our restricted domain over here. That's what we're going to need something going on over here where this kind of gets, all these positive values can come out of that. But I do, if I restrict x, if I say that x, in this case, this would be my restriction. This will work out, this will equal that if, these will be equal if I restrict and say x is greater than or equal to 0. Then I can drop the absolute values and I get x and x. So I had to restrict the, if you will, the range of g. Plugging this in, the range of g has to be restricted. So in terms of the graph of our function, let's see the picture. Remember, I just drew these pictures. You'll have these written up here. I'll remember those. But I'm restricting, if you will, right there is my restriction by the absolute value, because I'm taking the square root of a square, and I have to make sure that the square root only gives me the principal root. And I looked at the function over here. This is the one I have. This is the one I've drawn. This is my f of x. And I have it drawn right here. It is minus 1, something like this. And here's that g of x. Let me just plug it into your calculator. I'm plugging into my head calculator and getting an answer over here. X is equal to 0, yeah, something like this. Okay. But what I'm saying over here, and all this saying, I want to make sure x is always positive. So what do I really want? I only want this side of this graph. So x has to be positive. That's where I'm restricting my x over here and ignoring getting rid of that. And then what do? Well, again, I'm back to my same idea and approach of drawing the line y equal to x. I'm just showing where everything's connected with what we did earlier. Here's our line y is equal to x. And if I flip this about this red thing, flip it about here. Because if I kind of flip this thing about this side, you can see what's going to happen here. Flipping it around here, I would get this. This -1 goes down to a -1 over here, and it would come up this way. And if I flip this thing about that side, it will go this direction. And you can see they are indeed graphically inverse ones. I didn't draw them perfectly to scale. Not too bad, but you know, nicer when you can do that using a graphic utility. But it makes sense. And then you can see why you have to restrict this over here. Because if I didn't restrict this over here, and I flip this, instead of that, I would also get this. If I kept the blue line over here, it would look like that. That would no longer be a function anymore. So that my inverse, that g, my inverse, is not a function because it would not pass the vertical line test. So you have to understand all those parts of a function to make sure you can put everything together correctly. Okay, that's all it is. You have to do both of these. Sometimes one will work and the other will not. Both of those have to work. F composed with G or G composed with F. It can happen that one side will work and the other will not. You might see some of those on the homework as you go through that. But that's essentially everything that we need.